Hello and welcome back. In this video we're going to work a couple of problems from the section regarding energy, power, and work. You'll see I have some information up here on the board already, but let's just start back with our definition of power, which we just learned in the last video. Remember, power gets the symbol P, and it's the rate at which work is done, so work divided by time. A quantity we haven't really talked about before, but is a very simple quantity to understand, is efficiency. Efficiency gets the symbol E, little e, and it's just the ratio of useful energy out from a machine divided by the energy put into the machine. So for example, you plug in your toaster and you want to toast a piece of toast. The cord heats up as energy is moving along the cord. There's a lot of heat that is radiated out into the environment. Some of the energy that comes in from P&M is converted into actually cooking the toast, but a lot of it is lost. And so the efficiency would then be the energy that went into actually toasting the toast divided by the total energy that came from the wall to the toaster. So that ratio is just the efficiency of the machine, and different machines have efficiency ratings associated with them. This ratio of useful energy out to total energy in is going to be identical to the ratio of useful power out to power in. So either of those ratios can be used. We can talk about efficiency as a percentage if we would like, and that would just be simply taking either one of those ratios and multiplying by 100% to put efficiency in units of percentage. And so we'll see that in the first problem that we're going to be working today. So the two problems we're going to be looking at today are both from your OpenStax text. The first one's going to be 754 and the second one will be 756. So reading 754 to begin with. Calculate the energy in kilojoules used by a 55.0 kilogram woman who does 50 deep knee bends in which her center of mass is lowered and raised 0.400 meters. Parentheses, she does work in both directions, end parentheses. You may assume her efficiency to be 20%. Part B, what is the average power consumption rate in watts if she does this work in 3.00 minutes? So here's the information given from the problem statement. So first of all, we're given her mass as 55.0 kilograms, and we're told that the number of deep knee bends that she does is 50. So I'm using the symbol capital N to keep track of that number of deep knee bends that she does. We're also told the time at which she completes these 50 deep knee bends, and that's 3 minutes. And I just quickly converted that to units of seconds, which is our standard unit for time. We're told that the distance vertically over which she changes her center of mass, and I'm just giving that symbol H. I'm giving the symbol H to that quantity, 0.400 meters. And then her efficiency is 0.20 or 20%. So they gave us the efficiency in percentage, and I'm just simply putting it back into decimal, 0.200. In part A, we want to know the energy she exerts. It's the same as the work that she does, and that's going to be in units of kilojoules. And then in part B, we want to know what her output power is. So those are here's all the information given in the problem statement put in terms of symbols that we use. And so in part A, we want to know what is the energy or work that she does, specifically calculate the energy in kilojoules used by a woman. Okay, so we are told that her efficiency is 0.20, and efficiency keeps track of work out divided by work in. Specifically, we want to know the work in. We want to know how much work she does. So we want to solve for work in. Work in is equal to work out divided by her efficiency. So where does the rest of the energy go as she does these deep knee bends? Well, some of her energy goes into moving her mass up and down, right? And so that's her workout. And where is the rest of the energy that's coming and going to? Well, it's going into keeping her alive. A lot of energy is used to keep our brain functioning, to keep our organs operating, and so on. So 20% of the energy that she has is going into actually moving her center of mass up and down. So the workout, okay, so the workout is going to be the work she is exerting in doing these deep knee bends. And remember that she is doing work in both directions. So for every deep knee bend, she is moving her center of mass up and also down. So we're going to get a factor of 2 for each deep knee bend she does. And then this is going to be times the number of deep knee bends she does. And then the force she has to exert is against the force of gravity, her mass times the acceleration due to Earth's gravity. And then the height over which she needs to change her center of mass, h. And this is all divided by efficiency. So we know all of these quantities. These quantities are already given to us and have been put here symbolically to keep track of these numbers. So let's go ahead and just plug everything in. So when you take these numbers and plug them in, and I won't write them as I'm running out of room, but let's just go ahead and plug those into a calculator. So this is going to be 2 times n, which is 50, times her mass, which is 55.0, times the acceleration due to Earth's gravity, 9.80 meters per second squared, and then times the height that she is moving her center of mass. And then we want to divide that now by her by the efficiency. So this number gives us, and sorry, this isn't efficiency, this is work in. So the work in is going to be equal to 1.078 times 10 to the 5th, and this is going to be units of joules. And so this is the amount of energy that is the total energy keeping her going. Again, this is the energy going to keeping her brain functioning, to keeping her organs functioning, and to moving her center of mass up and down as she does these deep knee bends. We want to put this in units of kilojoules, and so let's go ahead and express that as 1.08 times 10. And I'm going to have 3 units are going to be sucked up into kilojoules, so this is going to be times 10 to the 2 kilojoules. So 108 kilojoules is the amount of energy coming that she is supplying in total to keep everything going. So now in part B, we want to know how powerful she is. So she's able to keep all these systems going as well as also moving her center of mass up and down. So how much power does her body have? So what's her power rating? So the power that she experiences, and this is the power, her power in. This is not the power associated with her just doing the deep knee bends. This is the power to keep everything going. So this is going to be the total work or energy coming in divided by the time. And so this is going to be our 1.078 times 10 to the 5th joules. And we're going to be dividing that now by the time it takes her to do these deep knee bends and keep all her other systems sustained. And so dividing this energy by 180 gives us 599 joules per second, or watts. So 599 watts or joules per second. Remember, they are the same. So this is an example of how to use efficiency and also how to use how to distinguish the total power coming into machine from the useful power that is being applied to a specific task to accomplish something. So That wraps up 754. Now let's go ahead and do 756 to apply these same concepts again. So 756 reads, the swimmer shown in figure 744 from the textbook exerts an average horizontal backward force of 80.0 newtons with his arms in each 1.80 meter long stroke. A, what is his work output in each stroke? And B, calculate the work output of his arms if he does 120 strokes per minute. So here I've written down some of the important information, and notice that the force he's exerting now is a horizontal force. He is laying on the water, on the surface of the water, and he is exerting his forces horizontally. Well, actually, the force is being exerted vertically and then horizontally, but his displacement is only horizontal. So the part of the force he exerts horizontally, 80 newtons, and the displacement horizontally, 1.80 meters. And then the two quantities we want to find is what is his work output. Notice this isn't the amount of energy that he needs to sustain his brain and his organs and all the other functions going on while he's swimming. This is just how much work output does he experience. And so that's the actual physical movement of his arms and his body along this displacement. And then in part B, what is his power output if he completes a certain number of strokes per minute? So let's go ahead and start with A. A tells us that, and in A, well, first of all, A, we want to know what the work out is. So work out is going to be equal to the force exerted dotted into the displacement. So the displacement here, we're using the symbol x, and in the problem statement, we're told this is the horizontal component of the force. So this is the horizontal displacement, this is the horizontal component of the force. They're in the same direction, therefore the dot product is going to give us an cosine 0 or 1. So this is just going to be equal to F, and for displacement I've used the symbol x here, so F times x. So the work out is going to be equal to the force, which is 80.0 newtons, times the 1.80 meter displacement horizontally. And when you multiply those two numbers together, we come up with 144. And the units we have are a Newton meter, which is also a joule. So 144 joules is the work output from each and every stroke that he completes as he's swimming. And then in part B, we want to know the power out. This is not how powerful he is, because remember, he's still having to sustain his brain function and his organ function, as well as his swimming. So we're just looking at the quote unquote useful power as far as getting from one end of the pool to the other. So the useful power, or the power out, is going to be equal to the work out divided by the time. So we're told how many strokes per minute as far as the rate at which he's completing strokes. So we know for each stroke, the power required is 144 joules, and he is completing 120 strokes per minute. So this is 144 joules per stroke, and that stroke doesn't need to be plural. I can just, there we go. Okay, and now notice that we know the amount of energy he's exerting per stroke, and we know how many strokes he completes per minute. Notice that the strokes are going to cancel here, and we're going to have joules per minute. This is not the standard unit. We want to have joules per second for standard units, so we're going to need to convert that. So the power out is going to be equal to 144 times 120. I'm just going to put all the units out here in front, or sorry, in the back, joules, and this is going to be per minute. And now we want to multiply by 1 minute is the same as 60 seconds. And so now the minutes will cancel, and now we're going to have units of joules per second. So let's go ahead and calculate that number. So that's 144 times 120 and divided by 60 is going to give us 288 joule per second is a watt. 288 watts, and so that is the useful power out, quote unquote, to get him from one end of the pool to the other. So here's a couple of examples that are similar to some of the homework problems you'll be working in class and also outside of class, and so please ask questions if you have any uncertainty about anything we did here, and we'll see you next time. Thank you.